Astronomy is a study of stars, the galaxies, and how the universe works. And mathematics plays a very important role in enabling the astronomers to identify how the universe works. So here's an example where mathematics has helped us to discover a planet itself. Yes, that's right. Now here's how it goes. William Herschel, using his telescope, observed the night skies. He made observations, and through that he discovered Uranus, the seventh planet from the sun in our solar system. So Uranus was discovered through observation. So astronomers, they worked out the math and found the orbit of the Uranus. But there was a catch. The orbit that was observed for Uranus, it didn't match with the orbit that was predicted by the math. Now, astronomers came up with many ideas to rectify this problem. So one clever manipulation was they worked out the math and predicted that there must exist a planet beyond the orbit of the Uranus. And if that exists, this orbit mismatch would be resolved. And hence, they theorized that there must exist a planet beyond the orbit of the Uranus. So the astronomers pointed their telescope towards the sky, and there it was, Neptune, the eighth planet from the sun in our solar system. The Neptune is the planet which was discovered from the mathematical theorization initially and then confirmed by observation.
Why did the apple fall down? Rather not sideways or upward.
This thought of Newton inspired him to think about gravity, and next he went on to do the mathematical formulation and got a gravitational force formula. After many experiments, Newton came up with the universal law of gravitation, which states every object in a universe pulls the other object with a force which depends on two conditions. First, the mass of the object. Second, the distance between the two objects. So now coming on to the mathematical calculation of gravitational force. He found that force is directly proportional to product of the mass of two objects and inversely proportional to square of the distance between them. And finally, he found a gravitational constant which all of us know, that is G. So the final formula what we got from Newton is that F is equals to G m1 m2 by r square mathematically for a gravitational force.
You see, the Newton's idea on gravity, it was a simple one. From the mathematics of Newton's formula, we were able to predict the motions of all the objects, for example, the moon, the planets, the stars, the galaxies. But the equation, it gave the influence of the gravity, but it did not tell us how this influence actually works. I mean, how the sun actually keeps the earth in its orbit. You say it's gravity, but there's no tether, they're not physically connected to each other. Then how does the sun exert its influence on the earth through the vastness of empty space? This was the problem with Isaac Newton's idea. It just could not explain the mechanism of gravity. So it needed the brilliance of Einstein to resolve this problem. Einstein's mathematical formulation to describe how gravity works is described in this equation. So he used the concept of tensor calculus to describe how the geometry of space-time depends on the matter that is present. The left-hand side of the equation tells about the curvature of the space-time, which is nothing but the geometry of space-time. And the right-hand side of the equation, it tells about the mass and the matter energy, which is causing this curvature. So this is how Einstein came up with the equation for gravitation. So here's a two-dimensional analogy of Einstein's idea of how gravity works. Now, when there is no mass on the space-time, the space-time fabric is nice and flat. So when an object moves through it, it follows a straight line. But when you consider a case where there is a mass in the space-time, the space-time fabric is curved. It's warped and curved. So the curvature will be
dependent on the mass that's present on it. And now when an object moves through such a curved space-time, it follows the curvature and moves in a curved path, and it no longer follows the straight line. So this is how gravity works according to Einstein. So the gravity is the result of the curvature of the space-time, and it's a consequence but not a force.
We all know that Einstein gave an equation saying how gravity works, and that is over here. At the same time, another astronomer called Edwin Hubble, he through his observations said that these galaxies are moving apart in the universe. But since Einstein believed in the static universe, he did not agree with the Edwin Hubble. Later on, some other scientists showed through their mathematical equations that the galaxies are not moving apart. Instead, the space between them is expanding. That is, as t tends to t0, that is, from present time to the next time, then the distance between them is increasing. And the mathematics, what they gave was this, which says that the distance between the galaxies is increasing, which says the universe is expanding.
Consider this balloon as a universe, and the dot on this, consider these dots as galaxies. Note the distance between these dots. Now if I blow this balloon, then note the distance between these dots again. Now you see the distance between these two dots has been increased, but this dot has not moved with respect to this dot. So how is it possible? Tell me. It can be only possible when the space between these two dots will increase. So the space between these two dots has been expanded. What do you think the black holes are? Well, they are the dead remains of the massive star. Their gravitation pull is so high, not even the light can escape from their boundary. The boundary of the black holes are known as the event horizon of the black holes.
Consider this. What happens if I throw this ball up? It goes up and comes back to my hand. I throw this ball with more speed. It goes further up and comes back to my hand. Now I want to throw this ball such that it never returns. Let me try. The speed with which I threw the ball is known as escape speed on Earth. And this speed on a black hole is greater than the speed of light. Now, this is why nothing can escape a black hole.
We saw the parts of the black hole. The two parts which we generally observe is the point of singularity, where all the mass of the black hole is assumed to be concentrated, and the other is called as the event horizon, which is an imaginary boundary, and it's also known as point of no return. So let's see how the math explains the black holes. This equation is known as the Schwarzschild metric, which describes the space-time around a black hole. Now, you can notice from this equation that when I substitute r as 0, we get a form as rs by 0, which is same as any number divided by 0, and that point is an infinite undefined number. Similarly, when rs equal to r, I again get a form as 1 minus 1 is 0, I get a form 1 divided by 0. So r equal to 0 and r equal to rs, I get an undefined solution to this metric, and that is projected here. So r equal to 0 is the point of singularity, and r equal to rs is the event horizon. So it's general conception that black holes are formed when nature divides by 0. And nature divides by 0. So Utkarsh, what do you think? How can we know what's happening in the distant galaxies? We can't go there, right?
Right. So maths is a tool which helps us to explore the infinite cosmos.